Now I'm going to discuss about the generalized correlation for gases. Before going to this topic, first I will summarize. I will tell you the significance of compressibility factor Z. So actually Z is it is a ratio of the actual volume to that of the ideal the gas volume. So it tells us about the ideality of the real gases. How much deviation the real gases, how much deviate from the ideal gas behavior. So Z equals to PV by RT. This is generally the compressibility factor is defined by this expression Z equals to PV by RT. And one more important important one is Z. The compressibility factor value is different for the different the fluid. Why? Because the fluid the pressure, temperature, and volumes are different. So therefore they have different the fluids. But at one condition, this Z value is same for all the fluids. At so that conditions is at reduced temperature and reduced pressure. So reduced temperature and reduced pressures are the mathematical it is given by T by the Tc and P by the Pc. So P by Pc is the produced pressure and T by Tc is the reduced temperature. So at the same reduced temperature and reduced pressure, all the fluids having the same compressibility, the factor. So this is called as the theory of corresponding states. So and here so Z is a function of Tr and Pr, and at these conditions the ideality of the all fluids are about the same. The deviation is the same. So the theory of corresponding states theorem is all fluids having the same Z value at the same reduced temperature and reduced pressure, and they exert the same degree of idealization. So now, this is true only for simple fluids like xenon, krypton, and argon. So suppose if you take the complex fluids, this is the deviation is not exactly same. So therefore, some researchers worked and they found that by adding an additional parameter, so the compressibility factor is the same. So that parameter is omega. So this is the 3-parameter model. So if you consider the same omega is called the eccentric factor. At the same eccentric factor and at same the temperature and pressure of all the fluids having the same the compressibility factor, and they show the same degree of deviation from the ideality. So that is the law of corresponding state, 3 parameters. So Pitzer and co-workers, they developed one equation. Pitzer and co-workers, they conducted several experiments and they found a relation for the eccentric factor. So omega equals to minus 1.0 minus log PR sat at TR equals to 0.7. So this is the general equation used to find out the eccentric factor. So eccentric factor at the same eccentric factor and reduced temperature and the reduced pressure of any fluid, the compressibility factor is the same. So by using these equations, the Pitzer and the co-workers, so they developed some correlations for gases, the real gases. So the first correlation is first they conducted several experiments and found that Z is a compressibility factor and Z equals to Z0 plus omega Z dash, and these Z0 and Z dash, so these values are found by experimental the results by conducting experiments, they found the Z0 and Z dash values for different fluids at reduced temperature and reduced pressure, and these Z0 and Z dash values at different TR and PR is given in the appendix in the Vanna Smith textbook. So this is the first correlation. This is called as a compressibility correlation. Z equals to Z0 plus omega Z dash. The generalized correlation for the compressibility factor chart. And later, same the Pitcher correlations, they developed second correlation. So we know that from the virial equation Z equals to 1 plus Bp by RT. So this is the virial equation, the two-term virial equation, and B is the second virial coefficient. And if you represent this equation with P as PC and PR and T as TC, TR, the equation becomes 1 plus BPC by RTC PR by TR. So this BPC by RTC is represented with the B cap. So Z equals to 1 plus B cap PR by TR. And the Pitzer and co-workers, they developed a relation for the B cap. This is called as the second correlation. B cap equals to B0 plus omega B dash. Here the B0 is a function of temperature only. Therefore B0 and the B dash, these are also functions of temperature only. And if you substitute this B0 plus omega B dash in this equation, so Z equals to 1 plus B0 PR by TR plus omega B dash PR by TR. If you equate the generalized compressibility relation and this relation, Z0 equals to 1 plus B0 PR by the TR. Similarly, Z dash equals to B dash PR by the TR. And the B0 and B dash, these B0 and B dash values, so B0 equals to 0.083 minus 0.422 by TR whole power 1.6, and B dash is 0.139 minus 0.172 by TR per 4.2. So this is the second correlation developed by the Pitzer and co-workers, the second virial coefficient. So Z0 equals to 1 plus B0 PR by TR plus omega B dash PR by TR. B0 PR by TR is nothing but Z0, and B dash PR by TR is nothing but Z prime. So and the B0 and B dash, these are the functions of the reduced temperature. So 0.083 minus 0.422 by TR per 1.6, and B dash is 0.139 minus 0.172 TR per 4.2. So now coming to the generalized correlation based on the second virial coefficient. So the third virial coefficient. So now take the virial equation of three-term virial equation of state. That is Z equals to so the three-term virial compressibility correlation for the third virial coefficient. So we know that Z equals to 1 plus B by V plus C by the V square. This is the truncated virial equation, and we also know that Z equals to, that is nothing but PV by RT, or V equals to ZRT by P. If we substitute these volume in the equation, Z equals to 1 plus BP by ZRT plus C P square by ZRT square. And now P equals to PCPR and T equals to TCTR. So Z equals to 1 plus BPC by RTC PR by TR into Z again, and CP square CPC square by RTC square PR by ZRTR whole square. And this BPC by RTC is nothing but B cap, and CPC square by RTC square is nothing but C cap. So Z equals to 1 plus B dash PR by TR into Z, and this is C cap PR by ZRTR whole square. So the second virial coefficient is found with the help of the second the correlation, that is B cap equals to B naught plus omega the B dash. Similarly, the C cap is a function of temperature there, and the Pitzer and co-workers, they developed a relation for C cap equals to C naught plus omega C dash, where C naught and C dash values, so those are given by C naught and the C1. So these are also functions of the temperature. So these are given by 0.01407 plus 0.02432 by TR minus 0.00313 by TR per 10.5, and C prime equals to minus 0.02676 plus 0.05539 TR per 2.7 minus 0.00242 by TR per 10.5. So with the help of the C naught and C dash, you can find out the C cap value, and then Z equals to 1 plus B cap PR by TR by Z plus C cap PR by ZR TR whole square. We will get the compressibility factor. So these Z equals to Z naught plus omega Z dash. This is one correlation, and then the second this is called as the compressibility correlation, and the second one is Z equals to 1 plus B cap PR by TR. So this is the second correlation, and third correlation is 1 plus B dash PR by TR into Z plus C cap PR by TR Z TRZ whole square. So this is the third generalized correlations.